Welcome back, everyone. We've talked about linear equations in the first two sections, and we're going to extend our talk about real numbers and make that into the complex numbers. Now, one thing to remember is that even though they're called complex numbers, it's just a name. It's an expansion on the real numbers that we're familiar with. So let's get my pen rolling here. There we go. Double check. There we go. I'm going to mark. So we're just about on our way. Okay. All right. So we're looking at something that caused a little bit of a problem a few hundred years ago. Notice that equation. It looks like a simple equation. There should be a solution to it. However, no matter what real number you put where the x is, you can never end up with a -1. That's really confusing. So, what mathematicians sometimes do is, if you don't have a number, throw in a number. And for some reason, because they didn't think it belonged, they called it imaginary. And they used the letter I to represent it. Now, two things you want to remember. First, I represents the square root of -1, even though it doesn't seem to make sense to our logical self. Remember that. But also at the same time, remember what that says about I. It means when we square it, we get -1, something we can't do with any other real number. But remember both those concepts because they're both handy when working with complex numbers. So, what do we have for complex numbers? Well, the complex numbers are going to look a little bit different. We're going to put it together with real numbers a and b, and the b part is going to be how many imaginaries we have going along with the a. So it's like having two hands. One hand has the real part, one hand has the imaginary part. Together they make a complex number. Remember, a is the real part, b is the imaginary part. Now, a little bit more paperwork for us. Two complex numbers, a plus bi, c plus di. How can they be equal? They can only be equal, as we mark by this equation, they can only be equal if the real parts are equal and the imaginary parts are equal, as we're saying over here. The a and the c have to be the same, and b and d have to be the same. They're like separate but equal in a way. Now, a little bit more. If you think about it a bit, if you have that complex number a plus bi, if the b part, this part right here, is 0, then this part is 0, and all you have is a real number. So for b equals 0, you've got the regular real numbers again. So the real numbers are a subset of all the complex numbers. Now, if a is 0 and b is not 0, then you have the opposite situation. Pure imaginary. There's no real part to that complex number. So, written away, this a plus bi is in standard form. So when you're working with complex numbers and you come up with your final answer and it's a complex, make sure it's in this format. The real part goes first, the imaginary part with the I goes second, with a plus between them, unless the b is negative, of course. This is a visual representation of how all the numbers go. So down here we have the natural numbers, that's counting numbers, 1, 2, 3, 4, 5, and so on. This is just a sample. Whole numbers are all the natural numbers and 0. So that's 0, 1, 2, 3, 4, and so on. If you throw in the negatives or the opposites of each of those with the whole numbers, then you have the integers. We're just building on that. Then if we throw in what we call fractions, what are rational numbers, we've expanded a little bit further. But we've still left out a bunch of other ones. For example, x squared minus 2 equals 0. It doesn't belong to any of those sets of numbers. So irrational numbers are also included. Notice also not only square roots and cube roots and fourth roots and all those, but pi is one there too. Pi over 4, and just to add one, e, Euler's number, is also an irrational number, which means 7e is another irrational number. Now what we're doing is we're taking all of those numbers, numbers that make up the real number line, and we're throwing in some non-real complex numbers. So we've got ones that look like 7 plus 2i, and so on. Remember, the real part goes first, the imaginary part goes second to make up the complex number. Pure imaginary numbers have the first part missing, so you have just I type, almost like variables, 3i, minus 2/3 I, and so on. Notice over here, we have I before the square root of 5. And you might think, well, isn't that wrong? Well, the problem is that if you write it like this, with the I second, some people won't be sure whether the I is outside or inside the square root. To make sure there's no confusion, when you have roots like this or when it would be in doubt, put the I first. Okay, now the complex numbers, or the imaginaries in particular, have some special things going for them, and you have to be a little bit careful when you're playing with them. So here we have the square root of the opposite of a. Now this doesn't mean that this number in here is negative, but in this case we're going to say it is. That way we can just talk about this, and this always represents a negative number. Then the number inside the root will be a negative, which means we'll have a complex number or an imaginary number. And what you do is you split that up. If you put the square root of -1 times the square root of a, that's the same thing as what we've got here. And remember, this part is I, so there's a good way of expressing it, putting the I first so that we know the I is outside the square root. Next, can you do this one? Hit pause and see if you can do this one. Okay, you're back. So, how would we do this? First of all, factor out the square root of -1. So, your first job is writing this. We'll fancy up one here, and the square root of 16. Okay, now this part actually comes out even. So 4, and since there's no confusion, we'll just make it 4i. We'll put the I second. And that would be the square root of -16 in its simplified form. So maybe you can take this ways too. Pause. First job, factor out the square root of -1. And we've got this. Now, just in case, we should investigate the square root of 70. Let's look at it up here. What's 70 look like? It's got several prime factors. You can factor a 2 out of this, a 5 out of this, and a 7 out of this. Well, unfortunately, none of those comes out even. So we'll just leave it as a square root of 70, and our answer will be I square root of 70. Follow? Okay, so when you do get something like this, investigate and see if there are any factors of 70 that are squares. As in this one. Factor out that square root of -1. We know that's going to be I. So we put an I there. Now the 48. Is there any square that divides into 48? Well, one possibility is 4 times 12. But actually 12 can be factored by 4 too. So 4 times 4 times 12. Oops, 3, excuse me. Better yet, 4 squared times 3. This part will come out even. So what we'll do, here's our square root of -1. And we're going to split this up. We're going to put the part that comes out even first. The square root of 16, that's 4 squared. And the square root of 3. Now, what do we have? Well, this part right here comes out even, so we have 4. This part is an I, and here we have square root of 3. And there's your answer for the square root of -48, simplified. Next, we'll move on to products and quotients. We've actually used part of that already. Always factor out that square root of -1 before you move on. And remember what I said at the beginning? One of those fun facts you want to remember, because it's very handy, is that I squared, the imaginary number squared, is a -1. Keep that in mind. That's going to come back again and again, so make sure that's really solid at the front of your brain. So, here we go. Now, it says, be extra careful. When you've got negatives in here, some bad things can happen if you're not careful and you follow the wrong rules. Now, whoever made these slides had a mistake and I couldn't fix it. This represents times. Somehow it didn't come out in the PowerPoint and I wasn't able to fix it. Keep in mind that the product of these two is the square root of the product. Real nice. Be careful though if you have something like this. You have what's going to be an imaginary first, an imaginary second. Remember, this is times. And if you're not careful, you can mess this up. So take this first part, square root of -4, simplify that to 2i. There's the times again. This simplifies to 3i. There's the 3i. Put that together, you've got 6i squared. And remember, I squared is a -1. So you've actually got 6 times -1. So the answer is -6. Now what you don't want to do, put a frowning face on this one. Don't multiply those together like this. Remember, this is multiplication. And bring those together like that. It looks like things are going to turn out just fine. But it doesn't work that way. Because when you multiply those two negatives, you get the 36. and everything goes downhill from there. 6 is not the correct answer. So factor out the i's first, 2i and 3i, before you go about any multiplication. Got that? Factor out that square root of -1 or I first. Excuse me. So how's this go? What do you think? Well, you got the square root of the same thing. Remember, we've got this goofy multiplication. Write them in terms of I. And this did get a little bit cluttered, so I square root of 7 times I square root of 7. So you've got I squared, and square root of 7 times square root of 7 is 7. And I squared is what? -1. And there's your -7. And that's what you should get. Remember what not to do. Don't multiply the insides first, because that'll cause errors. Another one to try. Again, multiplication. Try to fix those as we go, but just keep that in mind, because I can't do it all the time. So factor out that I first. So you have I square root of 6 times I square root of 10. Then you can put those together. You've got I squared because you've got I times I, and square root of 6 times square root of 10 will be the square root of 60. And you might be tempted to say, oh, I remember this is -1, so this will be negative square root of 60. So far, so good. Except 60 has a square as a factor. 60 is 4 times 15. So what we need to do is switch this to square root of 4 times the square root of 15. This part right here is just 2. So our answer is -2 square root of 15. That's our real answer. Okay, looks like the PowerPoint guy got it okay. We'll move on. Next. So, this time we've got a quotient. Why do we have a quotient? Because the fraction bar means divide. We're dividing what's on the top by what's on the bottom, as you would if you had 20 over 4. That's 20 divided by 4, which is 5. This is the same thing. And also what we just learned in the last slide is don't multiply those negatives inside. Don't divide them either. Get the I out first. So you've got the square root of -1 times the square root of 20. On the bottom, square root of -1, square root of 2. So we've got I square root of 20 over I square root of 2. The i's, just like anything else, can cancel. We get 1 there and 1 there. That's good. And since there are no negatives inside here, we can divide the 20 by the 2 and get the square root of 10 for our final answer. You might want to hit the pause button and see if you can do this. This should be a pretty simple one, I think. Hit the pause and come back. Okay, let's assume you're back. First of all, we're going to take out that negative, so that'll give us I square root of 48, and on the bottom, just the square root of 24. So the I is going to stay there. I. Now what about the square root of 48 over the square root of 24? Well, we can just divide those as usual and keep the square root. That'd be the square root of 2. There's our final answer. remember, factor out the I first. Don't multiply and then look to take out i's. That doesn't sound bad, taking out i's. Well, never mind. A little joke, I guess. Bad joke. All right, can you write this in standard form? First thing you want to do is split this. Remember, this represents division, so this represents -8/4 plus the square root of -128/4. It's the distributive law for quotients. So, what do we get? Well, the first one's pretty easy. No i's involved there, so we've got a -2. Done. Over here, let's see. Well, first of all, we're going to take out the I first. Square root of 128 and 4. Now 128 can be divided by a perfect square. Now what's the biggest square that will divide into 128? Well, after a little bit of thought, perhaps you come up with I square root of 64 times the square root of 2/4. And let's take a shortcut here. What is the square root of 64? Well, that's really an 8. And we've got a 4 down here, so 4 into that is 1, 4 into that is 2. So our answer is, remember, we didn't divide in the -2. We did that at the very beginning here. So we've got -2 plus I, 2i, because we've got this up here, square root of 2. Let me rewrite that for you. -2 plus 2i square root of 2. There we go. The moral of the story is, or one moral of the story, let me get that out of the way. Okay. One thing you have to watch out for when you're doing canceling like this is sometimes when you're canceling like that, you lose track of a number that's up here. So make sure that either you rewrite it several times or you keep very careful, close notice of what numbers are still up there. And there we go. Next. Well, if they're numbers, you should be able to do some operations on them, right? Well, addition and subtraction, they're brother and sister, right? Addition, no problem. We can add those. Here's our addition. And to do that, it's a little bit different. What you do is you take the real parts and add those together. And that goes on the left. And then you add the imaginary parts separately, put those on the right. So for example, if we have 2 plus 3i, and we're adding 7 plus 5i, what do we get? Well, the 2 and the 7 are real, we'll add those. So we get 9, and the 3i and the 5i. Just like with x's, you would get 8x, but this is just 8i. It works the same way. That's handy. Subtraction, same deal. We'll put this down here. Let's say 2 minus 2 plus 3i, and we'll subtract this time. 7 plus 5i. So what do we have? This means we've got 2 plus 3i, and remember the minus out here means we're going to change the sign of both the 7 and the 5i. So I have minus 7 minus 5i. Now we'll take the real part. 2 minus 7 is -5. 3i minus 5i will be a -2i. And there's our answer. That's the, let's see, the difference for the second example. So How about you hit pause and try this one yourself? I've given you a good example. You could even backpedal if you want to and take a look at my example again and see if you can do this one. In the meantime, we're going to move ahead when you get back. So here we go. You're back, and here we've got our original problem showing right here. Make sure you copy it correctly. Take the real parts, add those together. Take the imaginary parts, add those together. And there's our final answer. How about difference? Can you do the difference now? If you missed on the last one, and you thought, I knew that, I could have done that, prove it by doing the difference one. Remember, that minus sign here is going to change the sign for both of those before you add those results together. So there you go. Put the real parts together, the imaginary parts together. And there's your final answer. Negative 10 plus 10i. Well, if you can add and you can subtract, why not multiply? Why not divide? Why not? Of course. Just remember, and I've mentioned this twice before, keep this in your back pocket. Whenever you see an I squared, think negative 1. With that in mind, let's take a look at this. So, remember, if you had a plus bx times c plus dx, you would multiply the a times both of those, and the bx times both of those. We do the same thing here. A times both of these, and bi times both of these. Here's the first results, multiplying by the a, multiplying by the bi. That's FOIL, just as you did before. Now you've got some parts that can be simplified a bit. You've got AC, you've got ADI, BCI. Oh, these are similar. They're I terms, they're imaginaries. And this one has an I squared. Remember what I squared is? It's right up here, in case you had forgotten. That's a minus 1. So this right here, if you're looking, is a minus BD. And that'll be able to be added to the AC. And you put those real parts together and the imaginary parts together. And there's your answer. It looks a bit weird. It's easier when there are actual numbers in there, aside from the letters that represent numbers. So for complex numbers, if you're multiplying, it'll be the product of the first two, that's AC, and then minus the product of the B and D, because you get the I squared, which gives you the minus sign. And then AD plus BC will together be the coefficient for the I, or the complex, or the imaginary part of the complex number. So give this a shot. Maybe you want to take a look at that, pause there, make a note, see if you can do this one. And I assume you're back, so we're going to play with this one. So there's my mark, okay. So we're going to multiply by the 2 first. So 2 times 3 is 6, 2 times 4i is 8i. Then I'll multiply by the minus 3i. Minus 3i times 3 will be minus 9i. And then we've got the minus 3i times 4i will be minus 12i squared. Remember, this is a negative 1. So what we have here is 6 from here and a positive 12 from here, because you've got minus 12 times a minus 1. So you'll be adding 6 plus 12 for the real part. So, oops, 6 plus 12 isn't 12, is it? It's 18. There we go. And we've got the imaginary part. Add those two together as you would if they were x's. Minus I, and there's your answer. And good, they got it right too. I guess we've got some smart people working the PowerPoints, even if they can't get multiplication correct. Now, how about this? Okay, does that throw you for a loop? Well, it shouldn't, because remember, this just means you're going to use this twice. So if you need to, just write it out twice. Multiply it out. So 4 times 4 is 16. 4 times 3i is 12i. And 3i times 4, another 12i. That should look familiar because we're squaring a binomial in a way. And 3i times 3i is 9i squared. I squared. So this actually becomes a negative 9, which can be added to the 16. 16 and a negative 9 give you what? A 7. And we can just add these two together and get 24i. And there's a shortcut way. That's the way I do it, because I know these two pieces in the middle are going to be identical. So when I multiply this times this, I can put a 2 out front because it's going to happen twice. Either way, you'll get the right answer. 7 plus 24i, which if you can look through the maze there, that's what we got first. All right, how about this one? And you're thinking to yourself, oh, I can do this one. Well, this particular product is here for a special reason. Because remember, in the last two, we ended up with something that looked like this. Remember, we had an I squared in there. It gave us another part for the real number. This is different. Now, if you remember, if we had x plus y times x minus y, remember what that is? That's the difference of squares. And what we've got here is you got the same number in the real part, the same number in the imaginary part, but with an opposite sign. So it's just like this. So what we should get is a difference of squares. So we'll square the first one, that's 36. And for the next one, it's minus y squared. What's minus y squared? 25i squared, the minus, right? This is a negative 1, so that turns the 25 into a plus 25. No i's left. Add those two together. What a surprise. It actually turns out to be a real number, even though you've multiplied two complex numbers together, expecting to get a plus bi version of something. Remember the shortcut, because that can make things a lot faster for you. And that is something you should know coming in to college algebra. One last thing before we leave. These two, if they have the same real part, same real, but these two are the same but different sign, that makes them complex conjugates. Complex conjugates. Make sure you pronounce that correctly. Complex conjugates. Another example would be 17 plus, say, 8i, and 17 minus 8i. I. Remember, it's the imaginary part that will be different from one to the other, and the real part will be exactly the same. So this is a shortcut. Multiplying complex conjugates, you end up with a real answer, a real number. Now, quotient. This is going to be perhaps the most difficult part, but it's not terribly difficult once you catch on to it. The reason we just multiplied complex conjugates, like the 8 plus 5i and the 8 minus 5i, is that, remember, this gives you 64 plus 25. So, remembering that, take a look at this fraction right here. This is a fraction we would not be expected to give as an answer to a question. Why? I'm going to rewrite it over here. 3 plus 2. Now that I is the square root of -1, so I'm going to write it in. Now on the bottom, we've got 5 minus the square root of -1. The reason we wouldn't leave this as our final answer is we've got a square root or any kind of root in the denominator. So we don't want to write it with a square root in the denominator, and that's what I represents. So what do? Complex conjugates to the rescue. So what we're going to do is something that sounds even more simple than it really is. We're going to multiply by 1. Now the denominator over here was the part that caused the problem. We can't give the answer like that because we don't want a square root in the denominator. So how can we do that? Well, looking just at the denominator, don't worry about the numerator, it's going to be fine. If we multiply this by its complex conjugate, the denominator is going to come out even, or a real number. Now, I said we're going to multiply by 1. Now this is a trick for the denominator, but to be multiplying by 1, we have to have the same thing on the top and the bottom. So take this, figure out what its complex conjugate is. That's going to go in the bottom and in the top. Now remember, this is just a 1, so when we rewrite this, we're going to have the same fraction, but in a different form. So let's see what we've got. Across the top, forget about the bottom for the moment. 3 times 5 is 15. 3 times I is 3i. 2i times 5 is 10i. 2i times I is 2i squared. On the bottom, the easy part. 5 squared is 25 plus 1, because we have minus I squared, but this I squared is a minus 1. So we get a plus 1. So bringing that down here, on the bottom, we've got 26. Done for the time being. On the top, take a look. We've seen some of this before. The 15 will be added to, what is this? This is -2. 15 minus 2 is 13. Then we'll add these together just like we would x's, and we'll get 13i. Now, this is almost our final answer, but this is a complex number. And our complex number should be written like this, in that form. So we need to split up, dividing both of those parts by the 26. So our answer will be 13 over 26 plus, oops, we have a typo here. It should be 13i. There we go. 13i over 26. So what do we get? Well, 13 over 26 is 1/2 plus 13 over 26 can also be reduced, and we'll have 1/2 I. This, believe it or not, is the same as this. Yes, it's like a Ripley's Believe It or Not, if you're familiar with that. Remember, take the complex conjugate of the denominator, put it over here, and on the top. Then just go about your business, split the two into the real and imaginary part at the end, and you're in good shape. And there we go. They got the final answer. Good. We'll give them a B plus. They're still messing up with the time signs. We won't give them an A on that. Check that. We can multiply the 1/2 plus 1/2 I. In other words, we're multiplying that times the original denominator to end up with the numerator. I'll let you figure that out for yourself. Or you can bring it into class and we'll talk about it, but not right now. Okay, how about this one? You look at that and you say, wait a minute, that's not what we just did. Well, not quite. But we can use the same rule. What we'll do is we'll get a little tricky. This is a complex number, right? What does the numerator look like? Remember, it's supposed to be A plus BI. So it'd be 3 plus 0I in the numerator. So what's the denominator? 0 plus I. Okay, now it should look familiar, maybe. So you need the complex conjugate. Here's the complex number. What's its conjugate? 0 minus I. Is it coming back now? Put the same thing up here and then do the multiplication. On the top, we know this is 0, so we'll just make it easy for ourselves. 3 times 0 is 0, 3 times minus I is minus 3I. Okay, and on the bottom we've got minus I squared. Well, remember, this is a minus 1. Minus 1 will cancel out this, and we'll get 3I as our answer. Another surprise. Remember that all of these you can go back and look at again, and you can try them yourself or just watch them again to get the technique down. So the quotient. So what did they do? You've got a minus 3I on the top. I'm not sure exactly what they're doing. It's another way of doing it though. Because what you can do for this one, this is a little trick. Because if you look at the denominator, if you just multiply that by I, then you won't have an imaginary in the bottom. And there's your other one, and there's your 3I over minus 1 minus 3I. But you can go back and use the complex conjugates, but this is just a little trick. Multiplying this I by another one is going to give you a real number. This has to be equal to 1, so you put the same thing on the top as you did on the bottom, and just multiply straight across. This means you divide the minus 1 and 3, get negative 3, and so on. Now we get to the fun part, I think, of I. So one of those things I begged you to remember is I squared equals negative 1. The other thing was that I represents the square root of negative 1. Well, using this fact, that means if you've got I to the fourth power, that's I squared squared. Okay, that's not a big deal. But this I squared is -1. So can I replace this by the -1? Square that. Oh my gosh, it's a 1. I to the fourth equals 1. Yes, no trick. I to the fourth equals 1. In fact, here are the powers of I. I, of course, is I. I squared is -1. Remember that. I cubed. Remember, this would be I times I squared. This is a -1, so you end up with negative I. And then I to the fourth is 1. Notice what happens, though. When you go I to the fifth, it's the same thing as I to the first power. Sorry about that. I to the sixth has one more I. It matches up with I squared. I to the seventh matches up with I cubed. I to the eighth matches up with I to the fourth. And if we went further, I to the ninth, what do you think that would be? I. I to the 10th, -1. I to the 11th, -I. And I to the 12th would be 1. It's a cycle. And that cycle continues indefinitely. So, you might want to pause and look over that. See, it keeps going from I to -1 to -I to 1. I, -1, -I, 1. So how about I to the 83rd power? Well, you don't want to go through this process until you get to 83. So how can you do that? Well, if you divided 4, because this, if you divided 4, where am I now? There we go. If we divide 4 into 83, what do we get? Well, 4 into 8 goes 2 times. 2 times 4 is 8, good. Bring down the 3, 0 times, and you got a remainder of 3. So all of these, the first 20 quadruples, just give you 1. And you've got an extra I cubed. And what's I cubed? Minus I. Oops, that's messy. There you go. You might need to think about that, but it's fun. It cycles in a cycle of 4, very much like the clock does. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then what? 13? Not unless you're military time. It goes back to 1. Back to 12 again. Back to 1, and so on. So keeping that in mind, plus here's an extra fact to remember, or not, because remember, as long as x is a real number, anything to the 0, almost anything to the 0 power is 1, as long as x is not 0 to begin with. So with that in mind, I to the 0 is also 1. That's pretty handy. So it follows along with what we knew previously. So how about this one? Can you crack this case? There's I to the 15th. So what we want is take as many 4s out here as we can, which would mean we could take 12 out and would have another I cubed. Now 12 is a factor of 4, so this whole thing right here is just 1. So we get I cubed. And if you've already memorized that previous one, you know it's minus I. If you've forgotten, no problem. Just split this into I squared times I, and the I squared is minus 1, so there's your minus I. Done. Okay, here's a curveball. Reminds me of a place where I jog sometimes. Curveball drive is where I start running. Well, this is definitely a curveball because you've got a minus there, and I haven't told you what to do with that. Well, what you can do, first of all, we're going to copy that. We're going to multiply it by I to some power that's going to give us a positive number for a power of I. Now I want to either put 4 in this place for the exponent. I want to put a 4 or an 8 or a 12 or a 16, some multiple of 4 to make this be a positive number. Well, 4 is going to work because when we multiply those two together, we add the exponents. We've got I to the 1, and that's just I. It's all over. Make sure this is a multiple of 4 though. And then you add the exponents to get this one. And if you remember that cycle, you'll remember which one you get with this exponent. Well, that's it, folks. Complex, not so complex once you get the hang of it. So give it a little bit of extra time. Come in with some good questions to class, and we'll see you next time. Take care.